All right, good afternoon, everybody. Thank you all for coming. So this is it. This is our last lecture for the semester. Just a couple comments before we get started with today's lecture is please just double check, if you haven't already, that all of your labs are appropriately marked as being checked off in our grade book, and if not, please let us know. And the other thing that I wanted to remind everybody of is course evaluations. If you can take a couple minutes to fill them out and give us constructive feedback, we take it very seriously and use it in order to try to make next semester hopefully even better. All right, so today what we're going to discuss is cache coherence. So we're kind of going back to along the lines of where we were 2 lectures ago, where we started discussing the kinds of issues that we have to worry about when you start to have more parallelism. And so what we talked about 2 lectures ago was that as you start to have multiple processes that want to share same pieces of data, we had to introduce synchronization as a mechanism of making sure that the communication between them is safe. And today we're going to take that a step further and learn about what does it mean to have cache coherence. So first, let's just talk about what do we mean about cache-coherent memory in general. So we're going to start off thinking about a memory that doesn't even have caches, and assume that it's got a number of FIFOs attached to it from different modules that can make requests to this memory, and then there's a response FIFO for every request FIFO. And this memory can basically pick and choose where it's going to take requests from, but you want to think of this memory as being instantaneous. So wherever it picks the request from, it's going to immediately give the response. So what does that mean? That means that if I do a sequence of memory operations from, different FIFOs, I might get a sequence that looks something like, store the value 10 into address 100, followed by, I guess we can stick to store word, followed by, store 5 into the same address. And then let's say that I do a load of this address. So what it means to be cache coherent is that if that is the sequence in which the memory accepted the store and load requests, then it must be the case that what it returns to this load is a 5 and not a 10, okay? So we basically say that now as we introduce caches into our system, you can have, hierarchical caches, but in order for them to be coherent, it basically means that they functionally behave exactly the same way as this monolithic memory. Okay. So let's start off by just, getting an idea for what can go wrong before we try to solve it, okay? So we said that we're now dealing with parallel execution. So that can take multiple forms. It can either be on a single processor that has multiple cores, or it can be on multiple processors. Either way, as long as you have this, big shared memory, the same issues come about. So suppose, that we have this system with 4 cores, each of which has their own private cache, and then they share this main memory. And now let's say that we want to do a sequence of memory instructions on these cores. And so we're going to start off, and core 0 is going to request a load of address A. And so it's going to talk to the main memory. Main memory is going to respond that the value of address A is a 2. And so it brings this value into its cache. And now it has that the address A has a value of 2. Okay, so now core 2 comes along, and it wants to do a store to that same address A, okay? And so it's going to store a value 3 to it. And so it's going to have now address A in its cache, but it's going to now associate a value of 3 with this, right? So now what happens when I do this, go back to core 0 and it does another load? What's going to happen? What was that? Yeah?
It's going to load the 2 from its cache.
Exactly, right? We learned that what happens with our cache is we're going to check, is the address that I'm looking for in my cache, it's going to get a hit, and so it's going to return a 2, when really we should have it return a 3. So the solution to this is to introduce a cache-coherence protocol, which is what we're going to be talking about today. So one way that I might have solved this problem and avoided getting the stale data is that at the time that core 2 decided that it wanted to write to the same address, I could have chosen to invalidate the value from core 0's cache, right? So then when it went to do its second load of address A, it now doesn't get a hit in its cache, and instead it would have to go back and get it from somewhere else. And so we're going to get into more details about that in just a bit. All right, so in order to have cache coherence, we have to make sure that we follow 2 rules. The 2 rules are the following. The first is write propagation, which basically says that when any of my processors do a write, eventually that write is going to become visible to all of my processors. And the second thing is what we call write serialization, which is that writes that are done to the same location must be seen by all processors in the same order, okay? So how do we go about, satisfying both of these rules? So we're going to start thinking about write propagation. So for write propagation, the most common method, and it's what we're going to primarily see today and what I just alluded to in the previous slide, what we use is a write and validate protocol. So the way this works is that basically when somebody wants to do a write, you invalidate the copy of that same address from everybody else's caches, and then you're free to do the write because you're sure that nobody else is going to then serve up a stale copy of that data. An alternative to this is what's called the write update protocol, and the idea here is that every time you do a write, you basically update all of your caches and your memory at the same time. So you can imagine that that's clearly more costly, and so that's not what we do most of the time. All right, what about write serialization? So there's essentially 2 main solutions for this as well. The first is what's called a Snooping-Based protocol, and that's what we're going to primarily focus on in today's lecture. Now, this model, as you'll see, kind of breaks down as you start to have a much, much larger system with many processors, but it works very well for smaller systems. Basically the idea is that there's a shared bus that all of the caches are listening to, and by doing this, they're essentially snooping on the bus and seeing what it is that the other caches are doing so that they can all stay in sync with each other. The alternative to this is a directory-based protocol, and this is a much more complex system. We're going to just touch upon it at the end of today's lecture, but the benefit of this protocol is that it's much more scalable than the Snoopy-based protocol. Okay. So let's start talking about what does it mean to have a Snoopy-based cache coherence. So essentially what our memory model looks like is as follows. You have, you guys see my mouse? It's a little tiny. You have multiple processes, and each of them has their own private cache. And then all of these caches are connected to a shared bus, which is also connected to the main memory. Okay, and so the idea now is, when we studied caches initially, we basically said, well, the cache is responsible for listening to the processor's requests, and so every time it gets a request from the processor, if it has the data in the cache, it's going to return it. If not, it's going to, follow up with a request to main memory, get the updated data, and then return it to the processor. Now, in a Snooping-based cache system, you actually kind of have two masters. So in addition to listening to all the requests of the processor, you also have to listen to all of the requests that are coming on the bus, okay? And so in order to actually keep our caches coherent, we need to make sure that we're actually, a slave to essentially these two masters. So how does this work? Well, so the first thing is that anytime a Snoopy cache needs to announce something to the other caches, the way that it's done is as a broadcast mechanism. So it's sending one message that is received by all of the caches. So by definition, when you're doing this, that means you can only have one message on the bus at a time, and so that the order in which the messages or requests appear on the bus is basically a total order that all of the processes see, and they're all going to be able to follow it. So, as I mentioned, each of the caches needs to listen to two types of requests. The first is the processor's load and store requests, and the second are things that it observes on the bus. And the way that we define how it listens to these and exactly what protocol it should follow is by creating a finite state machine, or an FSM, which has actions associated with the different state transitions, which tell the cache how it's supposed to behave. So today we're going to look at there's actually several different FSMs that one can use in order to achieve cache coherence in a Snoopy-based cache system. And so we're going to look at a few of them and what are their trade-offs and advantages and disadvantages of one versus the other. So to get started, we're going to start looking at this very basic protocol, which is just a valid-invalid protocol. So what does this mean? Here's my FSM. I have two states. I can either be in the invalid state or I can be in the valid state. So this is pretty similar to what we've seen in our caches so far, right? Where when we bring up our system, every line in our cache is initially invalid, and then as I bring data into it, I turn it to valid, and I can only get a hit when I'm in the valid state. Okay, so now let's take a look at what else this FSM is telling me. So if I'm in the invalid state, and the processor says, I want to load some location from memory, the way that that's going to be expressed is along this arrow here, I get a processor read request. Okay, so when a cache gets a processor read request and it was in the invalid state, then it's going to issue a bus read request. Okay, so it's going to announce to everybody that it's trying to do a read by issuing this bus read request. And initially, nobody has this copy, and so the main memory is going to respond to this bus read request with a value that that the processor is trying to load. Okay, so after doing both the processor read request and the bus read request, we're now in the valid state, and we have the piece of data that we want in our cache. Okay, now suppose that the same processor wants to do another load of the same location. In this case, I don't need to send another request on the bus because I already have the data in my cache and nothing's changed. And so if I get another processor read request, then I can just stay in this valid state and I immediately return the response for that location in memory, and this dash dash here means that I don't need to issue any command on the bus in response to this second or third and so on processor read request. Now what about if I get a processor write request and I'm in the valid stage? Well, if I get a processor write request, I need to make sure that just in case there are any other caches that are also in this valid state, because it's perfectly safe for multiple caches to be reading the same value. So now that I'm about to write to it, I need to let everybody else know that I'm about to modify it. Okay, so what's going to happen is when I get a processor write request from my processor, I'm going to issue a bus write request. Okay, so this is going to allow me to actually update the value in my cache. But what's going to happen here is with all the other caches is what's demonstrated here in this dashed line. So the dashed line corresponds to what it is that all the other caches are seeing. Okay, so as soon as the other caches see on the bus that somebody issued a bus write request, then what they're going to do is, if they had a valid copy of that particular address in their cache, they're going to go ahead and invalidate it. Okay, and so this ensures that that the other caches are not going to incorrectly respond to a load request with stale data. All right, and finally, you'll notice that this invalid FSM, it basically requires a write-through cache. Does anybody remember what it means to be a write-through cache? Yeah.
You can write directly to the memory.
That's right. Okay, so basically every time I'm writing to the cache, I'm also updating memory directly. And so this last arrow here is just indicating that in the case where I started off with an invalid and I wanted to do a processor write, I would just go ahead and write it straight to memory. I don't even need to bring it into my cache. Okay? So let's work through an example just to, make sure that we're comfortable applying this FSM to multiple caches talking to the same main memory and trying to access the same address. So in this example, we have just 2 cores, and we're going to start off, and core 0 is going to try to load address A. Okay, so it's going to issue a bus read request for address A, and the memory is going to see that, and it's going to respond with the value of address A. And so now the cache is going to be updated with the tag that says I have information about address A, the state, which is now valid, and the data, which corresponds to this tag or to this address, which is 2. Okay, so now my core 1 comes along, and it wants to also do a load of the same address. Okay, so what's going to happen? Is it going to send something on the bus as a result of wanting this load? Yes, and what's going to happen on the bus? It's going to send a bus read request, just like we saw for the first core. Okay, and so we see a bus read request, and again, what's going to happen is that the main memory is going to respond, and it's going to tell us that the value is 2, and that the state, and we can now modify our state to be a valid state. So now both of our caches have the correct value for address A. So now, if either one of these caches does an additional load of address A, at this point we don't need to issue any additional bus commands, right? We can just service the load request directly from the cache, because we have a valid value in our cache. We can just respond with it. Okay, so now let's continue this, and now let's say that core 0 comes along and it wants to do a store to address A. So what did we say has to happen if we're going to do a store? Yep.
Issue a bus write.
We need to let the other caches know, and so we're going to issue a bus write to let the other cache know that it needs to invalidate its location. So this bus write is going to tell this core that it needs to change its state to invalid. It's also going to, at the same time, write the updated value to our main memory, and it's going to write the updated value to our cache as well. Okay, so now we've modified our value for address A. When we're in the modified state, or it's only possible for one of the caches to have a copy of this data. And then we also saw that it's a write-through cache, which wrote the data to main memory as well at the same time. Okay, so now let's suppose that core 2 comes along, and now it wants to do a load of address A. So now what's going to happen? What's going to happen is that we need to basically issue a bus read, and the main memory has gotten the updated value, and so it's going to return a 3. Now we have both caches with a valid value again, and it's the updated correct value. Okay? So any questions about this VI algorithm? Yes?
Just one question. When core 1 issues a bus read, is it possible that cache from core 0, the cache from core 0 responds to the bus read, or like?
It is. It is, and we'll actually see some examples later where they need to respond. But so they'll both have the same answer. So whether the cache responds or the memory responds, you'll get the same response. But good question. Okay, so let's first think about what's wrong with this. What problems do I have with this simple VI FSM for my cache coherence protocol? Any ideas? What's happening every single time that I'm doing a write? Every time I'm doing a write, I'm doing two things, right? I am both updating main memory, and I'm issuing this broadcast command on my bus to tell everybody that I'm doing a write, right? So this is pretty costly if, I'm actually in a situation where I'm just doing a bunch of local writes and there's really no reason for me to transmit this information to everybody as well as to my main memory every single time. And so, there are protocols which are going to address this and try to do things a little bit more efficiently. So before we go to that, let's just sort of summarize what we've learned so far. So the first thing we learned is that in a coherent memory, all loads and stores have to be placed in a global order, right? And by having multiple caches, if multiple caches have the same address in their cache, then you have the possibility of getting into a situation where you have one value that's stale and not the most recent updated value. And so we're going to ensure that this doesn't happen by making sure that only one of our caches has write permission to a piece of data at any point in time, okay? And so this is something that we're going to follow even in the more complicated protocols, okay? So it's always going to be the case that only one cache is ever in the position where it's allowed to actually make a modification to a particular address. And so this is going to ensure that no other cache is going to ever have stale data because we'll always be invalidating the other copies if we're requesting to do a write. All right, so now let's talk about a slightly more complicated protocol, which is called MSI. So MSI stands for Modified Shared Invalid. And as you can imagine, the invalid basically means the same thing. It means just that you essentially don't have that particular address in your cache. Shared means that you're currently just reading from the cache, and so you haven't made any modifications. And so it's perfectly fine for multiple caches to have a shared copy of the same address in their cache. And then M stands for modified, which means that I'm actually doing a write to this location. And so I have to make sure that this address is invalidated in all the other caches. All right. So what does this MSI protocol give us that the VI protocol didn't? So recall that in the VI protocol we said that we had to do a write to main memory every single time that I'm doing a write, and I had to do a broadcast and snoop for every single write. Whereas in MSI, now I'm going to be able to support a write back cache. So remind me, what's a write back cache? Yep. Exactly. So now I'm not going to have to write to my main memory every single time I do an update. I'm only going to have to do it, when I evict a line from my cache. And that means that I can actually satisfy writes locally. I don't have to issue a bus write command for every single write that I'm performing. And so let's see, what the FSM for this MSI protocol looks like. So we have our three states, and let's start once again with an invalid state and see how this works. So if I'm in the invalid state, you'll notice that these orange lines, which are also the solid lines, those correspond to the processor-initiated transitions, and the blue ones, or the dashed ones, are the bus-initiated transitions, okay? So basically, the orange ones are the ones that correspond to my processor is making a request to my cache, and what do I do as a result? Whereas these blue ones are, what am I seeing on the bus caused by other caches, and how do I need to respond to it? Okay, so if I'm in the invalid state and I want to my processor wants to do a load, then I'm just going to issue a process read command, and sorry, the processor is issuing a process read command, which in turn is going to have me issue a bus read request on the bus, and I'm going to then move into the shared state. Okay? If instead of just reading, I wanted to actually do a write, or my processor wanted to do a write, then the bus action that I need to perform is called a bus read exclusive, meaning I'm requesting exclusive access to this address of memory, okay? And so if I do a bus read exclusive, then I can go straight to the modified state, meaning I am the cache that has permission to modify this location in its cache. Okay, so what happens to, all of the other caches which might have also been working, on the same address? So suppose that another cache had previously loaded, let's say, address A. So I had two caches in the shared state, and now cache 0 decided that it wants to write, and so it went into the modified state. So what do the other caches need to do? They need to invalidate themselves so that they don't serve stale data. Okay, so whether the other cache was in the shared state or in the modified state, as soon as you see a bus read exclusive request, you're going to go to the invalid state. Okay, so the two arrows that I'm talking about right now are this one, which is I was in shared, I see a bus read exclusive, and so I don't need to update anything in main memory, so I just go directly to my invalid state. The other one is this arrow over here, where I was in the modified state, meaning some other cache had written to this address. So before this new cache can request to write to this address, the first one that wrote to it better write its data back to main memory, okay? And so what it's going to do is, upon seeing this bus read exclusive, it's going to issue a bus write back request, okay? So it's going to write back its value that it wrote in its cache, and it's going to go then to the invalid state, so it effectively no longer has that address in its cache. Okay? So at this point, it becomes nobody else has a valid copy of that address in their cache, and so this new processor can safely enter the modified state, and it's the only one that is now allowed to actually write to this address. Okay, so once I'm in my modified state, if my processor requests the same address either through a read or through a write, I can just respond to them locally. Right? I can certainly read from my cache and provide the right data, but in addition, I can actually write an updated value to my cache, and I can keep doing this for multiple writes, and only when somebody else requests to write to the same address am I going to have to, follow this arrow here and actually write my data back to main memory, okay? So clearly this is going to be much more efficient. So the one last arrow we haven't talked about is, suppose I'm in the modified state and somebody else requests to read, not to write to this address. And so what I need to do there is I need to now make sure that all of the caches have this address in the shared state. And so the one who was in the modified state is going to have to write back the value that it modified, so that everyone will see the same thing, and it now goes into the shared state, meaning that it can no longer do writes to this address because it doesn't have, exclusive hold of this address any longer. Okay? Any questions about that? Good. Okay, so let's work, through an example with the MSI protocol. So once again, we're going to have, 2 cores, and we're going to do a bunch of loads and stores of this address A and see what happens. Okay, so we start off with core 0 trying to load address A. Initially, it's not in its cache, so it's going to issue a bus read request, and the memory is going to respond. It's now going to go into the shared state and have the value 2 in its cache. Okay. Now, core 1 comes along. It also wants to read this value, and so what's going to happen? We're going to issue another bus read request, and now we can have basically, as we mentioned, the cache or the main memory respond. And so we're going to get the value, which is 2, and now I have 2 caches. They're both in the shared state, and they both have this value of 2. So just like in the VI case, now if either one of these processors wants to do an additional load request, those can just be satisfied locally, and I don't need to issue any bus commands for loads. But let's see what happens, with stores. So now core 0 comes along, and it wants to do a store to address A. So what did we say is going to happen if we want to do a store? We have to change to be in the modified state. Okay, so how do we achieve that? Well, we're going to issue a bus read exclusive bus command. This guy is going to see this bus read exclusive, and it's going to invalidate itself. Okay? Then, once that happens, it's safe for this one to switch to the modified state and actually update its value. Okay? Now, additional loads and stores only from core 0 can continue to be satisfied locally, right? So as long as if I do another store in this cache, that's no problem. I can continue to do it and not involve the bus or main memory at all. Okay, so now let's see what happens when core 2 comes along and it also wants to do a store to address A. So now what has to happen is I have to switch this guy to no longer have the modified state, right? So the way that's going to happen is core 1 this time is issuing this bus read exclusive. Core 0 is going to see it, and that tells it, oh, you have to do 2 things. First, you have to write back your data, and secondly, you have to go into the invalidate state. Okay, so the write back of this data is going to update main memory, so it has the value 3 in it, and it's also going to let this cache read the updated value. And so at that point, sorry, I skipped a step here. So the next step was that this cache invalidated itself. And so now it's safe for cache 1 or core 1 to go into the modified state. So it goes into the modified state and it updates this address with a value that it wants to write to that address. Okay? And you'll notice, so what's in main memory at this point? What value is at address A? Yep, 3, right? So I haven't updated the 10 yet. The 10 is only in this, in core 1. Any questions about that? Okay, terrific. Okay, so this is basically summarizing what we said, which is that MSI lets the cache serve writes without updating main memory, and it's possible for main memory to have stale data as a result, but it's never going to be the case that if another cache then goes to read the value that it's going to get the stale value data. Instead, what's going to happen is the one that has the most recent value, the one that's in the modified state, is actually going to respond to any process read request that shows up on the bus, okay? And basically, it's kind of like a race condition, but essentially what happens is that the response from the cache is going to come back faster than the response from memory, and so the other cache is basically going to see the value that's in the cache that's in the modified state, and so it'll get the correct updated value. All right. One last transition. And so now suppose that we come back to core 0 and it wants to do a load of address A once again. So now what has to happen? This guy is in the modified state. This one is in the invalid state. What has to happen in order for him to be, core 0 to be able to do a load? What state do they both need to be in? The shared state, right? So what's going to happen is core 0 is issuing a bus read request. Core 1 is seeing this bus read request, and so it's going to write back its value of 10 to main memory, and it's going to now switch to the shared state. Then it's at this point safe for this guy to switch to the shared state as well, and it reads from the bus the value that core 1 just wrote back. Okay? And so now we're in the state where both of them have the value, they're both in the shared state, and they both have this most recent value, which is 10, which you'll notice hasn't necessarily made it to the main memory yet, but will because of this write back. Okay? All right, so what are the, some observations that we could make about this MSI protocol? Well, if we think about, atomic instructions, which were something that we said were really important when we were talking about synchronization, what was the behavior that we had to do repeatedly and we had to do in a safe way was to be able to read, modify, and write. Okay, so now if we think about, the MSI protocol, and if I'm trying to do read, modify, write, it's not, the FSM isn't right in front of you unless you have the handout with you. But basically, if you look back, what you'll see is that this requires 2 bus transactions, because what we do is we start in the invalid state and we first had to issue a bus read request, which put us, in order to read, when we're doing the read, modify, write sequence, we're going to first request a read, which is going to put us in the shared state, but then we're immediately going to want to write, and so that's going to make us switch from the shared state to the modified state, but the only way to do that is by issuing another bus request, which is going to say, okay, now I want to do a bus a read exclusive, and that's going to put me in the modified state. But if the behavior is that nothing else is coming between this read, modify, write situation, then I could have done this more quickly by issuing a single exclusive request for this address and gone directly into the modified state. And so in order to, basically people notice that this is a problem, and so they've developed, a slight modification to the MSI protocol, which is called the MESI protocol. And so now we have an E state in addition to the MSI state. And so the only difference with this protocol is that the E state stands for exclusive, okay? So this means that if I'm in the exclusive state, then I'm guaranteed that nobody else is trying to even read this value, okay? So let's take a look at how our FSM changes in order to go from MSI to MESI, okay? So most of this is the same. I'm not going to go through every single arrow, but essentially if you look at kind of the bottom left here, that's essentially our MSI protocol, okay? What's changing is that we've added one more state, which is this exclusive state. So now what's going to happen? Anytime I'm in the invalid state and I do a process read, then one of two things can happen. If nobody else is currently, looking at this address, then I go directly to the exclusive state. Okay? If there are other sharers, then on a process read, I'm going to go into the shared state. Okay? And what's the benefit of being in the exclusive state? The benefit of being in the exclusive state is that from here I can do process write requests without issuing additional commands on the bus. Okay, so this is a local write request, which is taking me from the exclusive to the modified state. And the one other thing that I'll point out here is that this dashed arrow here tells you that if you're in the exclusive state, meaning nobody else was sharing this value with you, but now some other cache came along and made a request for this particular address, then I have to get myself out of the exclusive state and move into the shared state so that I no longer think that I'm allowed to locally write to this address. Okay? Any questions about that? Good. All right. So that's it for Snoopy-based caches, and as I mentioned, we're just going to very quickly touch on, what's this other cache coherence mechanism, which is known as directory-based. Okay, so the main problem with the Snoopy-based algorithm is that it doesn't scale, right? Because we saw that all of our caches have to talk on this shared bus, right? And we can only issue one bus request at any point in time, and so the caches might be sitting there waiting for each other to get access to the bus. So as we want to scale to larger systems with more processors, what we do is we go to a directory-based cache coherence scheme. And the way that this works is instead of having a shared bus, you basically have an interconnection network that allows point-to-point communication, and you can do, multiple point-to-point communications at the same time. And so essentially, just at a high level without going into details, and if you're interested in this, you should probably take classes like 6A23, which is a graduate version of computer architecture. Oh, by the way, I did want to mention that if you enjoyed this class, there are a few classes you should consider moving forward. A good class is 6111 is one good class. It's a digital design class. class. There's 6175, which is Arvin's class, which will now be a new class as a result of the modifications that we've made to 6004. There's 6823, which is the graduate computer architecture class, and there's also 6375, which is the graduate version of 6175. So just, keep those in mind. Okay, so back to directory-based. So what's going on here? So essentially what we do is we divide up our memory into chunks, where each processor is responsible for one portion of the memory, and it's also responsible for keeping a directory with all the information about that portion of the memory. So anytime somebody makes a request for a particular address, they know which one of the processors is the one that owns that address. And so you essentially make a direct request to the processor that's responsible for that address, and it's going to look up in its directory what the state is. Is it in the shared state? Is it an exclusive? And so on. And it knows exactly which of the other caches have made requests for this particular location. So based on that knowledge, it's able to tell you to do the right thing, so that if somebody else is trying to do a write, then it will tell you to invalidate yourself. If somebody else is in the modified state and you come along and want to do a read, it'll tell both of you that you should go into the shared state, okay? And so the idea is really the same, except that instead of having one shared bus that everybody listens to, you can do these point-to-point communication, and then each processor is responsible for its portion of the memory, and then it knows everything. So it's essentially a central control for that portion of the memory. Okay? All right. To wrap things up, the last thing that I wanted to mention today is you'll see that, as we continue to talk about these things like, introducing parallelism, we keep running into new problems that we have to address, right? So we talked about synchronization. We talked about cache coherence. So there are more of these things that come up. And so I wanted to just, bring up one more to just get you guys kind of thinking before we wrap things up. And the issue here is what we call cache coherence and false sharing, right? So in today's lecture, we were constantly talking about cache lines holding a single address. But when we learned about caches, we learned that that's generally not what our caches look like. Generally, a cache line holds multiple addresses, right? And so imagine that you're in a scenario where one processor is writing, let's say, to word I, and the other processor is writing to word K. Now notice, these are two completely different words. They're different addresses. They shouldn't cause a conflict, but if they happen to map to the same cache line, then what's going to happen? What's going to happen is I'm going to constantly have to switch back and forth between which is the cache that has the right to modify this line, even though they're actually trying to write to two different addresses, okay? And so that's just, one example of additional problems that can come about once you start thinking about, all of this parallel execution. And so with that, I'm going to leave you guys. I'm going to wish you a wonderful summer. Last thing I wanted to say was just we're also always very interested in lab assistance for 6004. So if you like the class and might be interested in doing that, please reach out to me. And thank you very much. And I should, of course, say thank you to all our amazing staff as well.